Okay, welcome back everyone from the break. So our next talk is going to be another video presentation. This one is called Introducing Exact Match Hardware Offload for OVS by Farhat
Hello
Ullah
everyone.
and Farhan Tariq.
Hello everyone. My name is Farhatullah and Mr. Farhan Tariq is my co-presenter in today's talk. We are working together at Dreambig Semiconductor. Dreambig Semiconductor is a startup designing ASIC-based DPUs utilizing chiplet technology. In today's presentation, we will introduce a new feature for OVS that will allow exact match offloading, along with the rationale for its implementation. So let's start. The agenda for today's talk is briefly discuss a high-level overview of OVS architecture, discuss different hardware solutions available for megaflow support, especially TCAM and hash tables. We will walk you through the challenges associated with each available solution, followed by our proposed solution and its implementation. And finally, we will demonstrate how rules are transformed from megaflows to exact match rules, ultimately offloading to hardware via TC flower. Before diving into the problem statement, let's take a moment to review the current architecture of OpenVSwitch. The OpenFlow controller sends OpenFlow rules to the vSwitchD component. vSwitchD acts as the central control plane daemon. It runs the switch and performs several key tasks related to network virtualization, forwarding, and configuration. vSwitchD configures offproto with the OpenFlow rules received via OpenFlow protocol. offproto plays a key role in handling OpenFlow rules and managing the OpenFlow-based data plane operations. This component is primarily focused on flow table management and packet processing according to the flow entries defined by the controller or local configurations. When a packet arrives at the switch, offproto checks the flow table to find the matching flow entry based on packet header fields like MAC addresses, IP addresses, VLAN tags, etc. If a match is found, the corresponding actions are applied to the packet. For example, forward to a port, modify headers, encap, decap, etc. It communicates with DPF interface to install these entries into the kernel data path. If hardware offloading is disabled, the rules are handed off to the OVS data path module, which executes the flow rules and handle packet forwarding for the subsequent packets. However, if hardware offload is enabled, the rules are offloaded to the Linux TC subsystem, which allows advanced traffic classification and filtering directly in the kernel. TC subsystem also offload these rules to the hardware. DPF interacts with the kernel via netlink sockets. This presentation only focuses on OVS TC offloads, and DPDK RT flow is not covered in this talk. As we know, OVS offloads megaflows only to the hardware. To support megaflows, let's explore how hardware can effectively support megaflows. One possible solution is the use of TCAM, ternary content addressable memory. TCAMs offer extremely fast search capabilities, typically allowing for single clock cycle lookups. This speed is vital for applications that require real-time decision making, such as routing and switching. Unlike traditional memory, TCAM can store entries with wildcards, which enables flexible matching as you can see in the picture. There are zeros and ones, while X represents the don't care bits, also known as wildcard bits. This feature of TCAM is very useful to support megaflows in the hardware. Additionally, TCAM can perform simultaneous comparisons across multiple entries. This feature makes TCAM more powerful to efficiently search large data sets where many rules need to be evaluated concurrently. Another advantage is TCAM is especially effective for multi-field lookups as required by the OVS and advanced networking protocols. So TCAM allows to match packets based on multiple header fields simultaneously. Lastly, by offloading complex matching operations to hardware, TCAM reduces the need for extensive software processing, resulting in improved system performance. While TCAM offers multiple benefits, it also poses significant challenges, particularly concerning scalability requirements. One major challenge in implementing TCAM in networking devices is its limited size due to its design constraints and the physical space it occupies. This limitation can restrict the amount of data TCAM can store. As networks grow and demand for faster data processing increases, the limited capacity of TCAM can become a critical bottleneck, affecting the overall scalability of network systems. Additionally, TCAMs consume considerably more power than standard RAM. This high power consumption arises from the parallel searching mechanism that activates all parts of the memory during search. Increased power requirements not only raise operational costs but also lead to higher heat generation, which adds challenges for maintaining optimal hardware temperatures, especially in large scale deployments. Another issue is TCAM hardware is generally more expensive than conventional memory solutions, which can limit its widespread adoption. Furthermore, due to its complex design, TCAM cannot be easily scaled using external memory, which limits its flexibility in adapting to changing network demands. Therefore, based on the complexities and challenges associated with TCAM, its use in the DPUs and SmartNICs leads to several challenges. An alternate approach to support megaflows is to use hash tables. Since hash table is inherently designed for exact matches, effectively supporting megaflows requires creating separate hash tables for each unique mask. Each hash table will correspond to a specific pattern of wildcarded rules. Thus, a more structured approach is needed to account for the complexity of wildcard rules and unique masks. Before storing and searching in the hash tables, both the rule and key must be processed based on the associated masks. For instance, replace wildcard positions with a special placeholder or unique identifier that the hash function can recognize. The functionality of hash table works by searching the primary table. If the rule is not found, it then searches the second table and continues searching sequentially through subsequent tables until the desired rule is located. This approach of hashing can address the scalability and power issues, which are the main associated concerns with TCAM. However, hash tables can introduce several other issues and challenges to support megaflows. Let's talk about the potential issues associated to this approach. Each unique wildcard mask requires a separate hash table. Since OVS matches on multiple fields, the number of possible combinations results in extremely large number of tables. As a result, supporting a hierarchy with numerous tables to handle worst-case scenarios adds more complexity to the design and requires effective management of multiple hierarchical tables. Another drawback of this approach is sequential searching. This sequential searching can result in the significant delays, especially when many tables are involved, and it badly affects the performance. Each table may have its own set of entries and hash functions, requiring several checks before a match is found. Additionally, implementing priority based rules adds another layer of complexity to the design, as each table must support an efficient mechanism to determine which rule has the highest priority among potential matches. Based on the issues associated with megaflow support in the hardware, we propose a new feature to OVS that offloads exact match rules to efficiently support OVS operations in the hardware for maximum performance. Exact match rules are straightforward to implement, they are less complex, and most importantly, they are scalable as compared to megaflows. Since the OVS software path already processes open flow rules, megaflows, and packets, adding this new feature will not introduce significant issues in the overall design. On the contrary, it can help simplify many complexities in hardware implementation. From an implementation perspective, we initially developed a POC in the OVS user space and submitted as an RFC page. The community welcomed the idea and identified some issues in the first approach. Based on their feedback, we have revised the implementation. Let's review both the implementation in details one by one. In the first proposal, we didn't make much changes to the OVS. We have introduced a new flag for exact match offload, which is disabled by default, and the user can enable it at runtime when needed. To enable exact match offloads, the user must disable the megaflows. The OVS architecture is the same, only added few lines to zero out the unwanted masks if the key value is 0. From implementation point of view, this approach is simple and straightforward. There are no architectural changes in the OVS. The exception path, flow invalidation, statistics, and counters are not changed. The disadvantage of this approach is it requires to disable megaflows. As megaflows are imported in OVS for production environment, disabling it is not a good solution. Based on the feedback in the previous proposal, we are now working to change the implementation and keep the megaflows enabled along the exact match offloads. The changes we made are: a new flag is introduced to enable the exact match offload. By default, this flag is disabled. It doesn't require to disable megaflows now. This implementation has significant changes in the OVS architecture, especially in the flow of offloaded path. The changes in the architecture are: if exact match offload is enabled, the DPF block will hand it off the flow to the kernel data path instead of TC-flower. As OVS kernel data path contains megaflows only, an extended functionality is added which further translates the megaflows to exact match rules. After translating the megaflows to exact match rules, it hands over it to TC-flower internally within the kernel. As TC-flower can process the rules in software, that's why we are thinking to not introduce a new cache for exact match rules in the data path separately. There is no changes made to the TC-flower side. This feature will not introduce any changes in the packet miss path. We may need to update the counters, statistics, and flow invalidation logics. With this approach, we will leverage the megaflows of OVS as well as offloads the exact match rules to the hardware, which can be handled efficiently in the hardware. We are working on this implementation internally, and currently this work is in progress. Upon successful implementation and testing, we will submit the patch for review. We invite other NIC vendors to contribute in this feature to introduce a more generic solution to OVS and enhance the OVS support in hardware. Anyone wants to contact us can access directly on the mentioned emails in the first line. Once again, thank you so much. Let's see the functional demo of the changes we made to the OVS. I will invite my colleague Farhan Tariq to present a demo.
Hi, thanks Farhat. Before starting the demo, please note that this demonstration is currently running on Dreambig's simulation model. Also, this demo is based on the proposal 1. On proposal 2, we are currently working internally and are not ready yet, as mentioned by Farhat earlier. The left side window in the terminal represents the host OS where OVS and the simulation model is running. The top right terminal represents virtual machine 1 and the bottom right terminal shows virtual machine 2. To simplify the process, we have written scripts that automate the execution of the commands needed to set up the environment. Running the script dbmars_setup compiles the simulation model and executes it in the background. It loads the driver into the kernel. The setup demo.sh script performs the basic OVS setup. It creates 2 VFs and enables switch def mode. It configures and restarts OVS to apply the changes and also disable the mega flows. It creates an OVS bridge named BR and attaches the PF and VF representers to the bridge, as shown in the terminal. Finally, the bridge is configured with rules. As shown in the configurations, exact match offload and hardware offload flags are true, and mega flows are disabled. In the OVS bridge, the interface dbnix0 represents PF and the interfaces ETH0 and ETH1 are the representers for VF1 and VF2 respectively. These are the rules configured. For our packets, apply the normal action. Packets originating from the input ETH0 representing VM1's traffic with the UDP protocol and a source IP of 12.12.12.0/24 are redirected to ETH1, which represents VM2. In this configuration, the last octet of the source IP is wildcarded, and all the L2, L3 and L4 fields except for the source IP are also wildcarded. Similarly, another OpenFlow rule is added to the bridge to redirect UDP traffic with a source IP of 12.12.12.0/24 from the VM2 to VM1. In this case, all other fields are wildcarded. In the top right terminal, run the script start_vm.sh to start the VM1. In the bottom right terminal, run the script start_vm.sh to launch VM2. Assign the IP addresses 12.12.12.3 to VM1 and the IP 12.12.12.4 to VM2. The setup is complete here. Run tcbdump on VM1 to capture the traffic and run the script send_packets.py on VM2. Send_packets.py is a script that uses the scapy library to generate UDP packets. As captured by tcbdump, the packets are received by VM1 with the IPs configured on the both virtual machines. Now let's examine the offloaded rules using the tcfilter utility to see which fields are offloaded to the hardware. From the tcfloor rule, it is visible that the exact values for all the parameters such as destination and source MAC addresses, Ethernet type, as well as destination and source IP addresses and the destination and source ports are also offloaded to the hardware. Let's examine the relationship between the OpenFlow or off-proto rules added in the user space and the TC-flower rules offloaded to OVS. By comparing these two, we can clearly see how wildcarded rules in the user space are translated into the exact match rules and then offloaded to the hardware for efficient packet processing. By looking into the user space rules, it specifies that any UDP traffic from interface ETH1 with a source IP range of 12.12.12.0/24 should be forwarded to ETH0. This rule can be applied to any MAC address and UDP port if the source IP is within the given range. The following two packets are sent from the VM2 using SCAPE. The first packet is with the destination IP of 12.12.12.3 and destination port 0. The given destination MAC address is the VM1's address. The second packet is also the same as the first one, but the destination port is 1. The source IP address 12.12.12.4 matches the wildcarded source IP and the wildcarded UDP destination port in the given OpenFlow rule. Now, let's look at the corresponding TC-flower offloaded rules for this traffic. We have captured two TC-flower rules for UDP traffic with destination ports 0 and 1. Both the rules forward the packets to ETH0, which represents VM1 in the OVS bridge. By examining both the offloaded rules, we can see OVS offloads MAC addresses, IP addresses, UDP ports, and other TC supported fields. It offloads exact match values and there is no mask attached to any field. Another point is that OVS creates two rules from a single user space rule and offloads two separate rules. Each rule represents a single flow. It also shows that exact match flow offload feature doesn't introduce any change to the OpenFlow rules. However, it makes changes to the offloaded rules. It is worth mentioning here, as Farhad also highlighted, we are working on the second proposal. Any feedback is also welcome from the community in finalizing the exact match fields that should be offloaded. Thank you all. Any questions are welcomed.
Thanks very much. Our speakers are online to answer questions. So do we have any questions? Oh, Elko.
All right. Thanks for the presentation. So my main question is, what is the reason about reintroducing exact match? Because a long time ago, actually OVS was running an exact match system, and they were running a lot of issues, especially with flow explosion. So my question is basically, do you have a specific use case in mind for this? Because if I'm thinking about the Kubernetes or other use cases, this will, increase the number of flows in the data path, and we might get the old problems back again.
Hi, am I audible?
Yeah, we can hear you.
Yeah, thank you. Yes, I read the paper that initially OVS were exact match and then introduced mega flows. At that time, I think that was just user space to data path, and now we are trying to add exact match with the mega flows, so there will be no too much context switching between the kernel and user space. And from the user point of view, we have some users that requires it only exact match of loads in the OVS, and they don't need any wildcard. So we don't want to change the exact OVS architecture exactly, right? But we want to add an additional feature. If some users have to offload only exact match offloads, they can enable exact matches. Otherwise, the mega flows and the wildcard flows will work the same. And on the hardware side, we also support TCAM and mega flows. But we think, especially our hardware team, memory team, thinks that introducing the exact match with benefit in the performance, especially if multiple tables are involved. But currently, we don't have any performance numbers. We are just thinking from the design perspective and also some customers' perspective.
Okay, Elko has a follow-up.
So I would suggest just to try, rather than with a simple VM, I would suggest trying it with a Kubernetes environment just to see how many data path flows you'll get, because I'm quite sure you get a flow explosion where it becomes almost impossible to keep up with the number of flows being inserted and removed and updated, because you have so many exact matches. But yeah, others might have other experiences, but that is at least my experience.
Okay, thanks. I noted your point. We will try to see with Kubernetes. Thank you.
Okay, are there any further questions? Any in the meeting? Okay, well, thank you very much. Let's thank our speakers.
Thank you.